Okay, so let's talk about the photoelectric effect. Now, what happened was back in the day, about the 1800s, they discovered if you have a piece of metal and you shone light on it, then you'd knock electrons off and you'd get electrons flowing around the place. And basically this is the same principle that we use nowadays to generate light with photoelectric cells or silicon cells. So they discovered this in the 1800s. But they didn't, at that point they weren't quite certain how it worked. What they was using, they're using the classical theory caused by people like Maxwell. And basically it says if you turned up the, so what the assumption was at that point is if you increase the frequency, increase the amplitude, the intensity, then what you would get is you get more kinetic energy, more energy per electron. So basically they were saying if you turned up the brightness of the light bulb or brightness of the light source, that each electron would get more zip and more energy. And what this meant was that frequency was not important. So basically it said if you shone red light on there or blue light on there, it didn't make any difference, or UV light. And if the light source was weak, light source weak, then it could take quite a while for it's weak. Then it would take a while for the energy being absorbed in the metal to ping out an electron. So it would take a long time for current. However, in reality, they discovered that this was wrong. Because, I mean, these are predictions using Maxwell's equations and various other things, so you can go out there and you can test for them. And the answer was this correct? And the answer was no, these were wrong. What they discovered was that the kinetic energy depended on frequency. So the maximum kinetic energy, let's say the maximum kinetic, depended upon frequency. So blue light gives off a lot more energy. If you shine a blue light on there, you get more energy than if you shine a red light on there. And UV will give you more energy per electron. No electrons were emitted below a certain frequency. And we call that the cutoff frequency nowadays. What else did we know? Increasing the intensity, increasing how bright the light is, intensity, increase the current. So increase the number of electrons being knocked off, but not the voltage. And remember, the voltage is how much energy each electron has. So basically, if you shine a bright light on there, it would increase the current being generated, the number of electrons being knocked off, but not how much energy each electron has. And also, the time, even for weak light, the time was very short. Time to emit was very short. So what that was, so this principle here worked on the fact that light was working like a wave, like at a beach, or if you go down to a beach and see the waves coming in. But this said that hypothesis was wrong. So that meant that we had, as scientists and as species, had to choose a different way of looking at light. So along run came a guy back in the day called Einstein. And this is part of his 1905 work. And he was basically working with people like Planck and things, and said light is quantized. And basically what that means is it's emitted in packets, like little wavelets. Bump, 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 bump. Instead of being a continuous wave, you get these little BBs of light, ponk, ponk, being shot out. And he worked out that E, the energy, and this is actually one of the classic equations, in joules or electron volts, your choice, I've probably mentioned this before, is equal to Planck's constant, with me, yeah, constant, times the frequency, which is going to be frequency. So the frequency is in hertz or per second, so this is going to be joules per second or electron volts per second. So I've mentioned this before, just before. And we know that, so he also hypothesized mass of an electron, photons have zero mass, which, zero mass, well, as he's actually describing photons, so when we quantize light, we call the little packets photons. So photons have zero mass, or zero rest mass. They'll have a relativistic. So remember before we were saying E is equal to PC for a massless particle? So if we combine these together, we can say for photons, the momentum P is equal to H, Planck's constant, so momentum is equal to Planck's constant, H, over the wavelength, because the wavelength is the inverse of the, because remember, wavelength is going to equal C divided by frequency. So that's going to be wavelength in meters. So it's going to be meters, it's going to be, what do we say that, joules second, so that's going to be kgs, meters per second. So basically, when you have your surface like this with your atoms in here, these little photon packets will come in, bang, and knock an electron off. And that will be pretty much instant. It's like, yeah, you throw a heavy ball bearing or a brick at the wall and bits chip off pretty much instantly. So if you throw something heavy in there, this electron comes off very promptly, which explains this bit. And so what we can actually say is that for one of these collisions, or for any of these collisions, HF is going to be the energy of the photon, So basically, we set that up here, E is equal to HF, so the energy can be written as HF is going to equal the kinetic energy of the electron knocked off, because remember what we're having here is we're having this photon comes in, whack, so this photon is going to have energy of HF. This electron here is going to have kinetic energy, K, plus the work function. And basically, this is how much energy it takes to actually remove the electron. This atom is holding on to this electron. So, and we'll show that in the next section. So to actually release this electron, you have to supply some energy in here before it will actually get knocked off. So the actual amount of energy is the work function. This is usually a couple of electron volts or such like, or 1 electron volt, or even less, half. But this work function depends upon what the metal is or what the element is. So this we usually measure experimentally, but each different solar panel material is going to have its own different work function. So usually this is rearranged to give K max, the maximum kinetic energy that it can have, is equal to the energy of the electron minus the work function. And in the books, and that's the way that it's usually given. So you'll notice here though, the maximum possible kinetic energy, this is a constant for the material, so and this is a constant, Planck's constant, so that means K max is proportional to F. The higher the frequency is, the higher the higher the potential energy is. So you'll notice that the intensity of the light, the amount of light in there, does not depend, the intensity of kinetic energy does not depend upon the intensity but the frequency. So this says, the first model says the frequency was not important but the intensity was. This says actually that it's actually the other way around, so we get this. So no electron emitted below a certain frequency, that's our cutoff frequency, or work function, our cutoff frequency. Kinetic energy depends upon F. Yay, so this equation here explains why this is wrong and this is right. Isn't that cool? And the way that we work out what the work function is we go and we basically set it up and we ramp up the frequency. So we call this the frequency cutoff, or cutoff frequency. The lowest frequency that will emit photons is going to be the work function divided by Planck's constant. And that tells us, so light below that amount of energy is going to do nothing. Light above, or light below that frequency will do nothing. So if we draw this as a graph, what we have here is K max versus frequency. The line basically goes through here. So below a certain frequency, this is our cutoff frequency, below this frequency it's got negative kinetic energy, so it won't knock the electron free from the atom. But above this frequency, the harder you hit it, the more energy it gets. So this cutoff frequency, we can draw that graphically. So yeah, so this is K versus, and that's an F frequency, and this is zero kinetic energy, and this is going to be frequency cutoff. So yeah, now this work is by, as I said, Einstein. This is his photoelectric effect. And it was interesting because they had a problem. When Einstein produced the theory of relativity, the theory of relativity was so controversial that they didn't want to give him a Nobel Prize for relativity just in case it turned out to be wrong. I mean, if it turned out to be wrong and they gave him a Nobel Prize, they'd look like idiots. If it turned out that he was right, Einstein was right, and they didn't give him a Nobel Prize, they'd look like, the committee would look like idiots. So what they did was they actually gave him a Nobel Prize for this. And this experiment is one of the first experiments that proved quantum theory, because it says that light is emitted in is emitted in photons, which is a type of quanta which is what quantum theory is. The downside, of course, is that Einstein hated quantum theory. He hated the random nature of quantum theory. So you can just imagine how impressed he was for getting a Nobel Prize in physics in the subject that he hated the most. So, oh well, that's life sometimes.